Thank you. This presentation was part of the keynote address, if you saw that, from Dr. Shadaman. He talked about 3D printing. He was referring to the 3D printer I'll be talking about today. I want to thank my co-author, Felipe Escamilla. He did a lot of work programming computers, setting things up, working with this prototype 3D printer system that I'm going to roll out for you. Another note of interest is, I wasn't sure where to put this. 3D printing is a new, innovative technology. And you look at all the technical sessions, there was no place to put it. So I came into commercial because it is commercially available. So you'll see this kind of in a technical format. I apologize, a lot of people won't expect that in a commercial session, but just that was the deal. Little mention of my company, RDAbbott company. We use applied curiosity in what we do. We are a distributor, but more important than that, we're a full service supplier. We have a fully staffed lab of experts that can handle needs across the industry in rubber. Now, this is just today's curiosity, which is 3D printing. So, let me tell you a little story, because I always like to start with stories. So, think of Star Trek. Think of that thing they used to use in those original Star Treks, the replicator. Game-changing technology is when we change the way we do things. What did Amazon do to brick and mortar? 3D printing could be the replicator of the future that replaces Amazon. Now, we're at the cusp of this. I'm not trying to tell you that we're ready to build replicators yet, but we are coming along. Let me show you where we are. Let's start with why we need 3D printers now and where this goes. Give you a little background here. Think about the design process, particularly DFM, designing for manufacturability. It starts with the OEM, who has an idea, that goes to the tool maker to build some kind of mold, and then to the fabricator to mold many, many parts. That process starts with an idea of an assembly. Then the OEM has to think about part design of those individual pieces in the assembly. Then the first part has to be prototyped. And this is usually a repetitive function because design engineers aren't perfect, and sometimes there's iterations. And this can be an expensive process and very time-consuming. Then we move on to the cavity design that the tool maker takes on. The tooling expert starts to understand where the gate locations are going to be, maybe use software analysis to figure that out. And then, of course, we're going to go to full production tooling, multiple cavity designs, and all the headaches that imposes. And then finally, the fabricator looks at how to manufacture in a very reliable, repetitive, almost a robotic type method, particularly in high volume. But where does the 3D printer come into this process? Well, if we take a look at where the parts are prototyped, that's where a 3D printer can produce your first prototype parts. And when we do that, it has a tendency to reduce the steps in manufacturing, and we streamline, speed to market is improved if we can supplement the design engineering at the OEM with ready-to-make parts. Imagine the design engineer coming up with that design and pushing a button and sending it to the printer, just like printing a piece of paper, right? Now we can actually make a part. Well, 3D printing is not new. It's been around since the 70s. My paper details the history of 3D printing and where this came about. But typically, 3D parts are only printed for fit and form. They're kind of not really able to take the heat and the environment that the surface temperatures demand. Imagine an automotive seal, and you wanted to print it. Well, if you used a material that couldn't handle the temperatures, it would just melt away in functional testing. So here we're designing with liquid silicone rubber with all the true attributes and heat resistance that silicone gives you. So what kind of materials can we print? Well, we have low-grade and mid and high-grade plastics. We have metals that have been printed. We have concrete, we have ceramics, we have precious metals, wood, cellulose, and of course, living cells in the biology fields. But what about these thermosets, particularly the liquid thermosets? What about heat-cured liquid silicone rubber? That's what I'm focusing on today. And I'm bringing to you both a machine and a material that can make this happen. So think about the traditional processes where we have solidifying, lamination, and additive manufacturing. Those are the three standard recognized methods of 3D printing. And then, processes of printing. And there's 7 methods that come from those processes. Well, today I'm talking to you about some of the newest technology, even within this grouping, which is additive. And I would even purport that we have now moved from 7 general recognized methods to 8, because liquid manufacturing of thermosets is now available. So we look at where these come from. And German Wrapup is the company out of Germany, been around since 2010. They're in development of liquid additive manufacturing, okay, or LAM. This is a number of machines that they're putting together. And we have had the machine for just over a year, and we've been running it through a number of case studies. It's very important that we qualify the materials. If I say that the material for prototyping is reasonable for fit, form, and function, I better have some data to back it up, right? So I have that, and I'll be presenting that today. So there's a number of models, particularly the prototype machine has these printer specifications with a building volume of reasonable size, which allows us large enough to make ASTM slabs and buttons. It has very small increments in Z layer height and nozzle diameters that allow us to go to fairly fine definition in printing the part, as well as a printer speed that gives you an average size part in about 2 hours. So not fast. The newer machines that are going to come out, they're going to be faster, they're going to be more reliable, there's going to be better definition. But this first one, that's where we're at today. That's the starting point. So think about liquid additive manufacturing, and the best way I can explain it to you is caulking and pushing material, silicone putty kind of stuff out of the end of the nozzle. Well, we do that by hand, but of course the bead is irregular. It's large. CIPG gasketing's been around since the 80s. In fact, I worked on some of those processes back then. And this is kind of macro dispensing, large beads. I'm talking about micro dispensing and fully automated. And really, when we look at the size of the bead and the shape of the bead, we control that with unique viscoelastic properties of the material. I said I'm bringing to you both a machine and a material. Can any LSR be used? It's often asked. Well, yes, but you won't have the printer definition because we have to have the chemorheology of the material as well as the viscoelastic properties very well pegged and very much related to the software. So not every LSR works very well. And so we learned that very early on this work, and so we've developed both those material machine together. So the other thing that's often asked is this UV cured? Is this LSR analogous to an injection molded part? Because it has to, particularly in healthcare and medical grade, or if we're going to say fit, form, and function, that it really needs to have the same mechanisms of curing. Now, injection molded liquid silicone rubber is cured by heat, a hot mold, right? And so here we use a system of infrared heating, and we lay down each layer, micro layer, and we cure each layer one at a time with infrared heat. And we design the chemorheology of the material to match that heat input. So what's some of the parts we can make? I circled in red the one on top. That is actually, I'm going to call that our Z slab. So think about if I'm going to produce an ASTM slab, it's hard to produce it flat, right? So in the Z direction, I had to put a little curve to it. So that's a curved slab. And then on the very bottom, you'll see an ASTM button and an ASTM slab. Of course, ASTM slab look a lot like this, and this one was printed. So let's look at some video, because that usually speaks a lot about. One layer at a time, as I said. What you're seeing is the part A and the part B of the LSR being put through a dispenser, and then through a static head, and then through the nozzle, and laid down. This is real time, and it's being laid down to create this Z-slab configuration. And you see the layers being built up. And then comes along the phase where that layer is cured. That's infrared. That's heat. That's a 600K infrared bulb. And we cure within 12 seconds. It's a heated table and format, so we keep everything isothermal. As we build up the layers, each successive layer has the same heat input. These are all very important constraints with respect to the functional design characteristics. So let's get into the study. And really, this study is about a qualification study. It's really about taking standard, probably very boring materials or shapes like an ASTM slab, flat as can be, and a button, just a round piece. But these are test articles that are common to the rubber industry. ASTM D412, for example, D634 and others. So we have a lot of comparison data. And this is a common way to take a look at it. Now, so what we did was we compared printed slabs and buttons to molded slabs and buttons. And more than that, we printed in various directions. The XY version and the XZ version. So we essentially have looked at the physical properties, the functional characteristics in all directions of printing, X, Y, and Z. And I'll explain that. And also, just to prove that it is functional testable, we're looking at heat stability, printed versus molded, and water resistance, two very important properties of silicone. So we immediately noticed that as we set up the many different designs and trials for printing these systems, some things came out, like bead geometry is very important. Layer and grain directions, or anisotropic conditions of the material became very important. And reactive curing, the speed, the thermal inputs, we actually had a little fire in the lab. One of the designs overcooked the material, so that was an issue. So the software, as we were writing the software, we were testing way out to the extremes. Well, I guess we went a little too extreme one day. But, and then very important in terms of physical performance is the bead to bead. That's as layers of beads are laid down together. And also the layer to layer adhesion, which is each successive layer. Now notice they're different. The beads are cured together as raw, but the layer on top is cured to an underlayer that's already cured. So, you know, you start to realize there could be some problems here in functional testing. And so this is the areas that we were looking at. Now, we were able to make adjustments to these in terms of our inputs to the software based on the speed of the movement of the head to the extrusion speed. The print direction, of course, is programmable. Heating time and heating level was also there. And then dwell and knit time between each layer was also able to measure. So these were key variables that we set as standards in the software, and now they're optimized, and all future generations of printed parts will use these optimized conditions. So one of the things we found in terms of extruder settings was rectilinear infill, which I show here. The rectilinear, of course, is kind of a zigzag, you know, that's the way that we tend to make parts. What we also found is that the extrusion multiplier, imagine putting toothpaste on your toothbrush. You can dab it, and you can pile it up on the toothbrush, or you can move the toothbrush very quickly to the extrusion speed and string the toothpaste out and thin the bead, right? So what we found actually is as we change, we actually extrude slightly higher speed than we move the head, we're able to start to fill these, and representative D is more optimal than representative A. I think that graphically explains that. All right, so those were major settings that we programmed in. This is how we program it. Directionally, we also had to look at things like what if we fill one layer in one direction and then fill the other layer in another direction? Or do we use the same direction? Or do we use 45-degree angle direction? So all of those parameters were looked at. We also looked at, as I said before, the overfill, and we found already that the 125% overfill was right. And then we also looked at an overlap, where we actually designed so that the hemisphere of the bead was overlapping the second hemisphere of the bead. So all these geometries became very important. So let me explain the wrong way to do it. Notice that in this, we are going 45, 45, 45. And this is not as fast as the printer works. This is a time lapse. And you're seeing 2 hours almost in that period of time. So things were moving. So when we looked at this crosshatch, where the rectilinear pattern was 45 degrees positive, then 45 degrees negative, and then 45 degrees positive again, we made a very poor tensile property. And we started understanding the reasons for that, which I'll explain. Now, let's talk about the right way to do it. This is now a 0, 0, 0. The rectilinear pattern of the first layer matches the rectilinear pattern of the second layer with an offset of a half a bead. And therefore, we are filling in the valleys with the second layer that were created by the first layer. And in doing that, we make a very solid looking part. That part you see there is this part I have in my hand. And it's making a very clear and very, very reasonably strong and physical specimen for testing. All right? So these were some of the design elements in terms of creating the software and understanding how best to print these systems. Now, I said we were delivering a machine and a material. The material we're delivering is Dow's Ziebell 3D material, which is very unique, very studied, very understood, viscoelastic and chemorheology properties. And when we look at this material and we compare it to typical LSRs, you see very common properties in tensile, elongation, tear, compression set. All the same properties you would see from temperature ranges for service. Volume resistivity is tested to be the same. The hydrophobicity of the silicone remains the same, as well as ozone UV resistance, and it is a very clear material. This is heat cured. We can pigment it any way you want, but for the definition of this test, we kept the materials clear. Now, I want to talk about the configuration and the type of charts that I'll be showing you. So the configuration of a 3D printer has got the X, the Y, and then the Z in the up direction in this order. What you see is a radar chart, and I presented the data in this way instead of a bunch of tables or bar graphs, because what we're looking for is differences, where one line stands out different from the other line. And we know then that there are differences between what I'm comparing. If there is, in other words, an overlap of the radar plot, then there is no difference and it's the same. So our hypothesis in functional testing is it different? Yes or no? I would say in all these properties it's a no, but when we look at tensile and elongation and tear, we start to see some differences. So let's zoom in on that. We will. And when we zoom in on that, let's also understand something very important about the XY slab versus an XZ configuration. I said I would get to this thing called a Z slab. The Z slab is actually built in this direction and the XY in this direction, which allows us to start pulling tensile specimens, and just in accordance with ASTM D412, we print a slab and we cut with a dumbbell die these different configurations. We don't actually print it, we actually cut them out in these configurations. And so the A, B, C, and D configurations are listed here. And notice that we have two patterns. We actually have A and B pattern and the C and D pattern separated. Well, that's interesting. What that means is that silicone rubber, like all other rubber, is subject to anisotropic properties. Grain direction is very important. Even ASTM D412 says that you have to align the slab in such a way that you cut the tensile bars with grain. So what we're seeing here is just the difference between with grain and cross grain testing. And you would expect it to show up in the ultimate physical properties of tensile elongation and tear, and probably not in the bulk properties of modulus, okay, and durometer. And so the hypothesis says, well, there is some differences, but it's just due to anisotropic behavior, which exists in all silicones at any time. So the printer can't correct for the silicone material itself. And so this anisotropic behavior, if we focus in on it, we start to see this is just a focus in on the ultimate properties. And what we see here is there's a difference when you look at cross grain versus with grain. And as I depict here, the bulk properties of E1 plus E2 do not equal. I'm sorry, E1 and E2 do not equal. And with anisotropic behavior, then they don't equal here, they do equal here. I have a hard time seeing across the screen, sorry. So there is differences here, as we see. So here we are able to see that A and B is a with grain test and C and D is a cross grain test. And as that shows is that when we cut with grain, we have a stronger physical property. Now, take that to injection molding. We see the same thing there. In injection molding, we'll see a gate. We'll see material flowing through that gate. We'll see grain lining up within the injection molded part. So we actually see that when we injection mold a slab as well. So it's no different. It's just that our hypothesis is the same as injection molded. So I can say that it is the same as injection molded in terms of basic physical properties. So let's look at it a little bit deeper when we look at the print configuration study, and we look at again the way that this looks under post curing. And now we're just studying with grain performance in accordance to ASTM D412, and now we're just looking at post cure of molded versus printed. And when we look at that, we see very little difference. So taking out this anisotropic behavior issue, we have all the plots lining up very well. So now let's take a look at, now I put together a radar plot legend because we're going to be looking at a series of plots based on heat age stability and water immersion data, including compression set. Molded is always going to be the red line, okay? And the green line is always going to be the XZ slab. And notice the green line is over the top of the red line, so if there's equivalence, the red line disappears. Now, if we look at the XZ slab is in blue, and it covers up the green and the red line. So this is just a fake plot showing you how I've arranged this data so that it's quick and easy to see in the following charts. Okay, and then of course I show with you a standard ASTM mold. This is what we're comparing it to. So we were compression molding these type of materials. So if we look at the patterns and the way they look, We'll look at we'll look at printed versus molded, and we'll look at these configurations. And where we see red, we see some differences. Notice that this is no post-cure. Now, if you study this, you'll see that the tensile and elongation properties are slightly higher, and the modulus properties are slightly higher for the printed materials, which now I'll take you to a 4-hour at 400 post-cure, and notice the red disappears. That means that in printing, we're actually able to completely cure each layer better than when we injection mold or compression mold a part, and we have thermodynamic changes within the material and the chemorheology. The material doesn't quite cure in the middle. And so this tells us that the 3D printer produces a part that is fully cured because we're curing each layer in thin section. That's pretty unique for platinum cure or addition cure. When we use those types of systems, they don't produce gases, and the reaction goes to completion through hydrosilylation processes. So now let's switch to heat aging, 70 hours at 150 C. And I want to also highlight the compression set. Notice that the compression set is very similar. Now, compression set is typically used as a gauge for cure, right? High compression sets are under-cured. Well, we have now with a post-cured system, comparing printed and molded, we have very good reproduction of physical properties. Now let's take it all the way up to the 200 C level. And I'm sorry, I have to go to the next one. At the 200 C level, we now, no red. What we're seeing is physical properties that are all the way up to the design temperature for silicones. So one of the things we can do is call that a surface temperature that's typical with any LSR type material. Then lastly, we're going to look at water immersion at 100 C, boiling water, and we see very little red. So in terms of heat stability, in terms of physical properties, comparing printed to molded, we see very little differences. So the hypothesis stands that in comparison of printed versus molded, there is very little difference. And therefore, a design engineer should be comfortable printing a part and using it in the fit, form, and function of an assembly. Just want to talk a little bit about what's on the horizon as a wrap-up. There's new LSR grades that we're looking at under the Evolve 3D type product line. We're looking at both a 30, a 50, and a 70 durometer, as well as oil-added type materials, which is common in automotive connectors and those type of things. So they come in all kinds of colors. They can be custom made, and we sell them in those Simcoe tubes that are easy to install in the printer. And so this technology is available in terms of raw material. Now let's talk about 3D printing technologies. German Wrapup is building even a new material, a new printer that includes support materials. So our next series will be able to not just make simple geometry shapes, but complex ones with roofs and overhangs. And we'll be using a cellulose type plastic that is easily water soluble. So once printed, the silicone can be dipped in hot water and you remove the support cellulose material, leaving a crisp and clean silicone part of any complicated geometry you need. So this will be a dual type printer head material machine. And then of course the improved software, partially due to some of our work, and the nozzle size options for finer definition are all there. So this technology, as Dr. Shadaman mentioned, is ready now. Now. He said that's the good news. It is, and it is available through RDAbbott. And we do distribute and fully service this printer and this material, and it's available commercially. So in summary, I just want to say 3D printing is analogous to injection molding. It's really allows for fast prototyping and speed to market considerations. There's one additional item is that if the OEM has their own 3D printer, there's design authority, and they don't have to shop out the prototyping. So intellectual property remains very close to the vets. And then I just have to say, this is a crazy picture. I think there's a couple of these guys that are in the back. This is my crew, and Matt there is being thrown into the mill because he got best in class slab for his idea for printing this very particular one. And the mill wasn't rolling too fast. So at this point, I'll just say thank you and ask for questions.